All right. Okay, all right, chemistry 3111. So I'm a little slow on the draw there. What I said was today we were going to start by taking a look at question 19.73. And I realized that organic chemistry isn't an exciting subject for everybody. I'm not that crazy. But to me, when I was a student, this is kind of the part of the class where I started to realize that I liked it because I liked looking at different reactions and finding out different ways to make molecules. So I think with this one here, the first thing you've got to realize is the functional group you've got in this compound, okay? So in the final product, we have an acetal, right? This is an acetal. Remember, an acetal is when you have a carbon with two R groups, but then it also has two ethers on it. And so this carbon, it goes carbon, oxygen, carbon. This one goes carbon, oxygen, carbon, oops, carbon. And so you can see that that is an acetal. So if we just do a little tiny retrosynthesis, right, this compound would have to come from one cis 1,2 cyclohexane diol, meaning this compound right here, plus the carbonyl compound, which is just going to be formaldehyde. Okay, how do I know that? Because there's two hydrogens here, right? So that's my retrosynthesis of the compound. Sanika, I just saw your comment. That's cute. Yeah. All right. So this is what we have to do. So now the question becomes, well, how do we get from here to here? And hopefully you remember there's a couple of ways that we could do that. You can use potassium permanganate to do a syn dihydroxylation. I think the way that my students usually like to do it is to use osmium tetroxide, so OSO4 and NMO. Again, this is what I assume most of my students like to use, but you could use the other reagents that we used as well, like osmium and sodium bisulfite and things like that. But this is the one they like to use the most. And usually with the NMO, with the osmium tetroxide, we write osmium tetroxide. We'll put catalytic amount, and then I'll put NMO like that. There we go. So we end up with the syn dihydroxyl. So we end up with cis 1,2 cyclohexane diol. And then the last step is the formation of the acetal. Okay, so here's what we have to do. We have to add the carbonyl compound, which in this case is formaldehyde. It's the simplest aldehyde. We put an acid catalyst. So that's what the H plus in square brackets means. And then it's a convention that we write minus H2O, right? Because we're losing water in the reaction. Okay, now again, the only thing I would say about this reaction, I wouldn't say there's too many options for this one. The only thing is, yes, we did look at a couple of different ways of doing syn dihydroxylation, but I've taught the class for a long time, and this seems to be the one my students usually gravitate towards. So let's try the next one. 19.73 from Klein 4th edition. So let me just put the compound in here. So what would this be? It would be 1-bromo-2-phenylethane, I guess would be the name of that compound. And we're trying to change the carbon skeleton, that's for sure, because we're adding a few carbons here, right? If you take a look, I mean, let's just ignore the aromatic ring, right? This portion here has 2 carbons, right? Because the aromatic ring isn't changing whatsoever. Now we have 1, 2, 3, 4, 5, okay? So we're going from 2 carbons off of the ring to 5 carbons off of the ring. And as far as this synthesis goes, I would say in terms of retrosynthesis, the best option in my mind would be, you see where this double bond is here, the carbon-carbon double bond? I think the best retrosynthesis is like this. If we had the carbonyl, right? If we had this methyl ketone, right? We call this a methyl, right? CH3 ketone, methyl ketone. If we had that methyl ketone, then between here and here, all we would have to do is a Wittig reaction. If you remember, if we use a Wittig reagent, that makes a carbon-carbon double bond, okay? And so now it becomes a little less complex, okay? Tiny bit less complex, because now all we need to do is we need to add these 2 carbons, right? And I would say that a retrosynthesis of that would come from this aldehyde, okay, and a Grignard reagent. So if we could make, let's see here, I'll do it like this. I'll put it to 1, 2, there, something like this. And then I'll put magnesium bromide like that, okay? If we had that Grignard, then we could, it would do a nucleophilic attack on this. We'd end up with the alcohol, but we can oxidize that alcohol. So again, that's my kind of retrosynthesis that I came up with for this problem. And so let's start out by doing our Grignard chemistry. So the first thing we want to do is convert this alkyl bromide into a Grignard reagent. So we treat it with magnesium. I'm not going to write up every single intermediate along the way. In step 2, we're going to treat it with this aldehyde. If you remember, you could call this ethanal, is totally fine to call it that. You could also call it acetaldehyde. Acetaldehyde. And if you look, I think at the introduction of chapter 19, there's a little section there on having a hangover, okay? If you drink too much alcohol and you get a hangover, and acetaldehyde is one of the main culprits of providing a hangover, if that's the right vernacular, providing. Anyhow, there we go. So after we treat that with aqueous acid, let's take a look. So we have our aromatic ring. We have our 1, 2 carbons. Then we have 1, 2 more, and then we're going to have our hydroxyl here, right? Let's keep going. I kind of ran out of space the way I did everything. But the next thing you can see that we need to do is to oxidize with PCC. You could use Swern, you could use chromic acid, you could use Des-Martin priodenine, whatever. It doesn't matter. But that's going to give us the methyl ketone that we wanted. So the methyl ketone like that. And then the last section is going to be to do the Wittig reaction. Now, when you're doing a Wittig reaction, you don't have to draw the synthesis of the whole Wittig reagent. You can just assume you have that Wittig reagent. I'm going to draw the Illene form. If you tried this before class, and if you drew this form, the Illid form, that's totally fine, because remember, these are in resonance with each other. And what we do is the part that is attached to the phosphorus, we put that in the place of the oxygen. So we're going to end up with the desired product. So we end up with that carbon-carbon double bond. Like that. And there you have it, my friends. All right. As far as different ways to do this synthesis, I suppose there might be some other ways that you could do this, but I don't see anything that would be as efficacious as this method, okay? So if you're still, working on fleshing out the idea of the Wittig reaction and how to make a Wittig reagent and what a Wittig reagent is, be sure to know that, because you remember it was a Nobel Prize winning reaction. It's one of the most, like it says in the textbook, these aren't my words. It says one of the most important reactions in all of organic chemistry. In fact, when I did my job interview at UCCS back in 1970, I'm kidding, a few years ago when I did that job interview, that was my interview, is they asked me to give a presentation on the Wittig reaction. So very, very important reaction for chemists. All right, so let's move on from there. I think this one's a little less complex than the last one, but again, that's just my opinion. This is 19.73C. So we're starting out with this alkane, where you've just got an abundance of methyl groups, so 2 here, you've got 1 here, and you've got 2 here. So what would you call this? 1,1,2,3,3 pentamethyl cyclohexane would be the name of the compound. But anyhow, we're going to take that compound and we're going to alter one part of the compound. So these methyls stay untouched. Okay, nothing happens to those. And then we're going to build an acetal out here. Okay, so remember, this is an acetal. So you have to be pretty rock solid on your acetal chemistry. Now, when it comes to an acetal, we've only learned one way to make them. And so in terms of our retrosynthesis, we can figure this out really quickly. We can say retrosynthetically, sorry, that's an ugly drawing, but anyhow, you'd have to have this aldehyde, and then your diol would be 1,2-ethane, or ethylene glycol, sorry, is the name of this compound. 1,2-ethane diol is fine too, but the common name is ethylene glycol. So now the question becomes, okay, well, how do we get from here to here? How do we get from the starting material to that aldehyde? It's a good question, but can you guys tell me, and this is not a trick question, but it's a Friday afternoon, so assuming that everybody I'm hoping that everybody had some lunch, maybe you're Liver is working overtime, digesting. Could anybody tell what's the first reaction I have to do in this synthesis? No questions asked. There's one particular reaction that has to be the answer for the first reaction. Because, right, we're just starting with an alkane. Exactly. Thanks, Mustafa. I knew you guys would know. It's just bromine and light. Bromine and light. Like that. You light up my life, bromine. Okay, so anyhow, so we end up with the bromine like this, okay? Now, in this case, there's only one type of beta proton anyway. So you would want to use, you could use a hindered base or an unhindered base, but this carbon is so hindered already, I would just use an unhindered base to pluck off this proton and make the alkene. So we're going to use something like sodium methoxide. If you chose a different base, that's totally fine. But the main idea is that you want to make this exocyclic alkene. And then I think it becomes not abundantly clear, but hopefully you have an idea where to go from here. So the next part is going to be to do an anti-Markovnikov addition of water, because that will give us the alcohol out here, right, without this double bond. And then we can just oxidize that to a ketone, or sorry, to an aldehyde. And then we're off to the races, right? Then we're done. So let's make that alcohol. So we're going to use borane and THF. I'll bet that everybody has this reaction memorized. You're like, yes, Mr. Dion. I wake up in the night and say borane and THF followed by hydrogen peroxide. Yep, me too. All right, so we make the primary alcohol, which is going to look like this. We need to oxidize it. We're going to oxidize it. Again, you could choose a Swern. You could use PCC. You could use Des-Martin pyridinane. You can't use the chromic acid because that'll give you a carboxylic acid. But if you do a Swern, remember that's dimethyl sulfoxide and oxalyl chloride in the first step. The second step was triethylamine. That'll give you the aldehyde. So now we have an aldehyde, okay? And you can see that we have to react this with ethylene glycol, which is our diol. So what's that going to look like? Same thing as always, okay? We're going to write ethylene glycol. We're going to put a catalytic amount of acid. That's what the square brackets mean. And then we're just going to write negative H2O. And that just means we're losing water. And so our final product should look like this. We have our geminal dimethyl here, geminal dimethyl here. That's this carbon is this one here. Okay, then it's going to be attached to an oxygen. It's attached to another oxygen, and those two oxygens are tethered by those two methylenes, and that's the final product. Okay, I don't know if I can squeeze it all on the page, but that's the total synthesis right there. We start with the alkane. We treat it with bromine and light, then a base to make the alkene. Then we do an anti-Markovnikov addition of water to make a primary alcohol. We oxidize that to an aldehyde. I can erase that goofy carbon that I threw in there. And then we just make the acetal. Okay, so acetals. So what have we seen? Things that we can think about. Our acetals are very important. Wittig reaction, very important. These two things are not necessarily related, but they're very important. We'll just put here chapter 19. Chapter 19, acetals and Wittig. All right, let's try the next one, which is, what was it? I had it written down here. Oh, yeah, this one's making a cyanohydrin. So again, this is 19.73. This is D. So the author seems to have some kind of obsession with ways of making cyanohydrins. If I had written a book, I would have just given you one way to do it, probably. But he gives you like Avogadro's number of ways, but there is one way that's better than the other, so we'll go over that right now. So remember this functional group here. This is called a cyanohydrin, okay? And in terms of retrosynthesis, I'm sure you guys figured this out faster than I did, that a cyanohydrin has to come from the ketone. So basically, we need to figure out how to get from cyclohexene to cyclohexanone would be the name of that compound. So the first thing we're going to do is we're going to hydrate it. And there's no Markovnikov or anti-Markovnikov to worry about. So in this case, we can just treat it with some plain old H3O+, and that's going to give us cyclohexanol. Now we can oxidize this again with just about anything under the sun. You could use Des Martin. Let's use a big hammer here. We'll use some Jones reagent. So sodium dichromate, sulfuric acid, and water. Again, I'm really beating on it here to do that, but it gives you the idea. So then we have the ketone. And then I think out of all the different ways that he showed how to make a cyanohydrin, the best way is using potassium cyanide, KCN, and HCl, like that, okay? That way you avoid, the reason why this is good is because you avoid using HCN. Remember we said that this had a boiling point of 26 degrees Celsius. It's a really dangerous compound to use. So there you go. In fact, if you're working with cyanides in a lab, you have to put a special sign up on your fume hood to let everybody know I am working with cyanide. This is very dangerous, you know. So everybody's aware that you're doing that, and that is not a joke. Let's try another one. 19.73E. Give me a thumbs up. Everybody with me so far? I haven't asked you guys an abundance of questions, but so far the rationale seems correct to everybody. Okay, okay. 19.73E. I looked over. It's not a bad question. It's just that 90% of the question uses reactions that you've known for a long time. So, you know, stuff that you've known for weeks and weeks and maybe longer than that. Okay. But anyhow, it is important because we did talk about imines, right? This is an imine, aka a Schiff base, okay, which is what they used to call it. Now we just call it an imine, okay? But we went over imines in enough detail that I think that everybody here knows that to make an imine, you have to have a carbonyl, right? That's why it's in the aldehydes and ketones chapter. And in this case, since your R group is a hydrogen, right, in that case, you would use NH3, right? You would just use ammonia. It's like NH2, but your R group is not an R group. It's just a hydrogen, okay? So it's just plain old ammonia that you have to use in this case. So now the question becomes, you know, how do I get, from here to here? And again, it's just kind of moving a bromine around the ring, really, and then just doing some hydration and oxidation. So again, this is something I figured that you could all solve very, very rapidly. But the first step, like you guys told me in the previous one, is bromine and light. That's going to give us 1-bromo, 1-methyl cyclohexane. Now, in this case, you do have two beta protons, right? You have the red one and you have the blue one. You want to pull off the blue one. And so to do that, you're going to use an unhindered base like sodium methoxide or sodium methoxide, doesn't matter. Even sodium hydroxide is fine. And so that's going to give you 1-methyl cyclohexene. Now you can see we're getting closer. Let's see here. So now if we want to add the hydroxyl group over here, we're going to have to do an anti-Markovnikov addition of water. So step 1 is borane and THF. Step 2 is going to be hydrogen peroxide and sodium hydroxide. And that gives us this compound. So the alcohol, like this. Let's see here. I'm kind of running out of space. So I'm gonna finish it down here. The next step, I'll just use PCC to wrap it up, but that would oxidize to the ketone. And then to make the imine, so what were the steps, okay? So remember, this is the one where the pH is very important. You don't have to write that down. All you'd have to write is ammonia. You need a catalytic amount of acid, and you lose water in the process, and that is going to give you your imine. Okay, again, this is an imine. All right, there you go. So let's see if I can squeeze that all on the page. Okay, so first step is bromination, elimination with a unhindered base to give us the that would be the Zaitsev product, and then after that we treat it with borane, okay, to do the anti-Markovnikov addition, PCC, and then then we form the imine. All right, there you go. All right, let's try. I think this is the last one. I think it went up to F, if I'm not mistaken. Let me double check. No, it goes up to G and H. Sorry, my mistake. So let's do 19.73 F, 19.73, and this is F. There we go. So F looks like this. So we have the secondary alkyl bromide. And again, this is one of those ones where I feel like there are a couple of ways that you could do this. But there's one way that's certainly better than any other. And what's cool about this one is that we don't change the carbon skeleton. Like here you have 1, 2, 3, 1, 2, 3, 4, 5, 6. And here we have 1, 2, 3, 4, 5, 6. Okay, those aren't numbered in terms of nomenclature or anything, but you see that there's no change to the carbon skeleton. And so in terms of a retrosynthesis, I think the best retrosynthesis would be this. So if we have 1, 2, 3, 4, 5, 6, would be to have the primary alcohol, right? Because then we could just treat that with PCC or a SWERN, and we would have the aldehyde, right? It's pretty straightforward. So then the question becomes, well, how do I get from here to here? Well, I'll do one more retrosynthetic step in this case. If I had this alkene, right, then I could just do an anti-Markov. So I'll just put BH3 THF, right? I could just do an anti-Markovnikov addition of water. So now the question becomes, well, how do I get from here to here? So let me ask you guys the question. There's two types of beta protons in this molecule. So let's take a look. I'll put this one in blue, and I'll put this one in red, like that. If I want to pull off the proton in blue, and this is not a trick question, it's just kind of working it out. Yeah, Sanika, would I use a hindered base or an unhindered base for this one? You got it. What would you call that base? Yeah, absolutely. Absolutely, that's what I would call it too, is a hindered base. So what Sanika chose was, and she's 100% right, she chose T-butoxide, perfect. So that's going to give us the Hoffman alkene. And then she said, well, treat it with borane and THF, followed by hydrogen peroxide and sodium hydroxide. That's going to give you the anti-Markovnikov addition. And then the last step is just to oxidize it and then choose whatever you want. Let's try. Oh, Sanika said PCC, so we'll use that. Good. There you go. All right. Give me a thumbs up if you think you could solve that one. Or stop me. Is there any questions about that one? I feel like that's a good question. Reasonable, kind of gets into your Zaitsev and your Hoffman and all that stuff, anti-Markovnikov. There's nothing really new in this one, but it is a cool question. All right, I think there's two more. I can't remember if I finished them or not. I guess I did. All right, the next one is making an enamine, and so that's a good thing to take a look at. So this is 19.73 G, and this one covers enamine, so you're just starting with benzene. So we're going to have to delve into our chapter 18 reactions for this one. And we're making this enamine, which looks like this, but you can do a retrosynthesis of an enamine. And doing the retrosynthesis, what you would have to have in this case is the methyl ketone. So this is acetophenone, and then you would just use dimethylamine, okay? And then react those together with a catalytic amount of acid. So now the question becomes, well, how do I get from here to here? Well, hopefully it's still fresh in your brain that all you need to do is a Friedel-Crafts acylation. So a Friedel-Crafts acylation, right? Because that's an acyl group. So you're going to use acetyl. This is called acetyl chloride and aluminum chloride. And again, this is a Friedel-Crafts, not alkylation, but acylation, if you need to go back and review that. So that's going to give you the molecule you need, which is, again, acetophenone is the name of this compound. And so the last step is just going to be treatment with this is called dimethylamine. You need a catalytic amount of acid, and then we'll just subtract water. We lose water from the reaction. All right, one more, and then we'll wrap it up for chapter 19. But this is 19.73 H. Okay, this one's kind of funny. I mean that in a good way. So this one, we have 1, 2, 3. Okay, and then we're taking that interesting looking compound, and then we're making another interesting looking compound. Like, I don't like the word interesting. Can't it just be something straightforward? All right, there you go. So what I would say with this one, it's not abundantly clear. Really, when you first look at these, it's like, what's going on here? But you can see that you're making an acetal, right? Right, here's the acetal here. So in terms of retrosynthesis, you would have this diol, right, like this. Okay, that would be the diol, and then you would have formaldehyde as your aldehyde in this particular case. So then the question becomes, well, how do I get from here to here? Okay, and you can see that they both have the same number of carbons. Look carefully. 1, 2, 3, 4, 5, 6, 7. So here we have 1, 2. I'm really off left field. 1, 2, 3, 4, 5, 6, 7. So they both have the same number of carbons. So there's no change there. So there's no green yard or anything involved in this. But what if we did one more retrosynthesis? And let me show you what I mean. I'm going to move the formaldehyde out of the way. What if, come on, what if we had this? I can do better than that. What if we had the diketone, right? Because then we could just treat it with sodium borohydride or something, and that would reduce it down to the diol. Anyhow, it's an idea. Yeah, let's see here. All right, looks reasonable to me, I guess. Anyhow, so yeah. Yep, that looks reasonable. So then how do we get from here to here? How do we get to these methyl ketones? Well, if you remember, there was a reaction we learned back in chapter 9, which is where if you have a terminal alkyne, you treat that with sulfuric acid and water and mercury 2 sulfate, and that gives you the methyl ketone like that. And so that's all we have to do is take this compound and we're going to treat it with sulfuric acid, water, and mercury 2 sulfate, and that's going to give us this diketone. So it's going to look like this. So there's our diketone. Now we can reduce that with excess lithium aluminum hydride, or we could use sodium borohydride. So let's see here. Let's just use excess. We'll use 1 is excess lithium aluminum hydride. Step 2, we'll put H3O plus. That's going to give us the diol, like that. And then the last step is just going to be the formation of the acetal. So we need our formaldehyde, we need a catalytic amount of acid, and then we lose water. And that, all right. Just give me 1 second. Yeah, that's how they did. I just looked. That's how they did it in the textbook. That's what I think would be the best solution there. All right. Does that make sense, Sanika? The way I did it to you? Or anybody? Okay. Okay, cool. Yeah, I think that's the best synthesis here. So, just kind of reviewing all this stuff. I mean, there's a lot of reactions swimming around in your head right now. I mean, what did we cover? Acetals. Chapter 9 made an appearance, right? Lithium aluminum hydride. We discussed enamines. So, enamines. So, make sure you know about enamines and how to form an enamine. This one, 19.73. Not straightforward, but just involves PCC oxidation. Um, Also, question 19.73. So an imine is obviously very, very important to us. What else? Cyanohydrins. So you have to know cyanohydrins, and they don't go away. They come up in chapter 20 again. The next one, we talked about acetals. Then on the previous one, we did the Wittig reaction. So Wittigs are going to be very important. You see that Greenyards showed up in here as well. And then if we go back to the first one, well, again, acetal formation. So that gives you a bit of an idea of, the kind of complexity of synthesis. There's one more thing that just entered my brain, though, which is the first reaction, right? In this one here, 19.73G. Remember that, even though it's tough, you still have to be on top of your electrophilic aromatic substitution, too, from chapter 18. So you still have to be able to keep track of your activators, strong activators, weak activators, and all that good stuff. Anyhow, I'll stop talking about that. But there you go. That's the idea. There we go.